In this class, I am going to explain the continuation topic for the inverting and non-inverting amplifiers. In those topics, I am going to today explain about input resistance and output resistance. In these input resistance, I am going to explain these input resistance. I am taking the circuit which is having the input Vi and it is connected to the R1 resistor, and we have an op-amp which is an gain AOLVD, and the output resistance R output and the input resistance R input, and the VD is the difference between these inverting and non-inverting terminal, and the Rin is the input resistor connected here. So RIF is the input feedback. Generally we have connected feedback here, but in this input feedback is connected between input terminals and the output terminals. Input terminal is R1 and the output terminal is R output, that means V0. Here this feedback network is connected in the input side. For the calculation purpose, we are going to calculate the R input, that means feedback input resistor. Input feedback, we have to calculate input feedback in this. Later I am going to calculate the R output resistor. So input resistor and output resistor today I am going to calculate here. So feedback resistor is connected here, input for the calculation of an input resistor across the input resistor. So R1 is the resistor across the this Vi, and the Vd is the difference between inverting and non-inverting terminal, and the R0 is the output resistor, and the R output is the output resistor connected across the circuit, and the V0 is the output. So internal, it is the internal op-amp. So these are the components connected to the internal op-amp. So here I am going to calculate the RIF. I am going to calculate the input resistor. Input resistance for a feedback network. Here we are connected this feedback network for the input. So here input resistor RIF is equals to, I am going to calculate these R1 plus R input. R input is parallel to R input feedback resistor is parallel to input resistor. So I am writing like this: R input feedback resistance is equals to R input R1. R1 is the resistor connected across the input terminal, and also plus R input resistor is parallel to input resistor connected across this input. So here I have RIF is equals to R1 plus R input plus is parallel with R input resistor. So here, whereas these are the different resistors, why? Because this is the feedback resistor, this is a resistor connected across these input terminal, so it is a different resistors. So R input is parallel to R input resistor. So here I can write like this: R in feedback input is equals to, this is the feedback input. I am going to calculate this. So R1 plus I can write like this. I have an input. I have input RIP and R output. I have the R input and the R output formulas. R output values input. This is the input resistor impedance and the output impedance. Input impedance and the output impedance. So here I have the values for the input impedance and the output impedance from the Miller technology. I have input impedance value as input impedance and the output impedance from output impedance values from Miller technique. These are the formulas obtaining from the Miller technique. I have R input is equals to RF by 1 plus AOL. We already derived these in the practical operation amplifier. So here we already know what is meant by RF, what is meant by AOL, feedback resistor and the open loop gain. So R input is given as RF by 1 plus AOL from the Miller technology, and R output is equals to RF AOL by 1 plus AOL. Here we can get the R input from the Miller technology as RF by 1 plus AOL, and the R output is equals to RF AOL by 1 plus AOL. These are the standard formulas. You have to remember these formulas from the Miller technology. Input resistance R input and the output impedance is given as R output is equals to RF AOL by 1 plus AOL. So here we can simply substitute our R input and the R output to this. So we have an R input here. So simply substitute this R input here. Then we can get an RF. We have RF is equals to, or R input impedance is equals to R1 plus R input is parallel to R input. So R1 plus we can get simply R input means we have already R input. R input means R input from the Miller technology, RF by 1 plus AOL into is parallel to R. Is parallel to R. So here this is considered as, for the simplification purpose, this is considered as R1 and this is considered as R2. So we have when there is R1 is parallel to R2 means we can write simply R1 is parallel to R2 means we can write simply R1 into R2 by R1 plus R2 from the parallel formula. So R1 is equals to, R1 means here RF by 1 plus AOL, 1 plus AOL into R2 means Rin by, R1 here, R1 is RF by 1 plus AOL, 1 plus AOL plus Rin. We can get like this. So here R1, Rin, feedback input is equals to R1. We can simply write, we can get, here plus. So R1, we can get, then the feedback resistor RIF is equals to R1 plus RF by 1 plus AOL, 1 plus AOL into Rin by, you can get RF plus Rin of 1 plus AOL by 1 plus AOL. Simply you can cancel out these 1 plus AOL or 1 plus AOL terms, then we can get an OR input feedback is equals to, or and take this term to this side, RF plus Rin of 1 plus AOL, 1 plus AOL into RF into Rin. RF into Rin. Simply R1 by RF plus Rin of 1 plus AOL. We can get feedback impedance. That means input feedback, input resistance when connected in feedback. Feedback network. Okay na? So here input resistance, that means we already know here the feedback resistor is connected across input and output, but here the feedback network is connected across input. Why? Because we are going to calculate the input feedback here. So we get an input feedback as R1 of RF plus Rin of 1 plus AOL into Rin by RF plus Rin of 1 plus AOL. Then this is the term for the feedback input. Now I am going to explain about output resistance by using another network. So here we have an output resistance. We are going to calculate the R output. So here resistance R output. So here we have an voltage difference Vd and the voltage across this input resistance is connected here. Feedback voltage feedback at the output side. So IB is the flowing current here, and the R1 is a resistor connected across this output. So Vin is the input here connected. So here this is the RF feedback resistor connected at an output, and the R0 is the output connected across output, and the AOL-VD is the gain. You already know about this. Rn is the input resistance, and the V0 is the output voltage connected across the output, and the R output feedback is the ROF. So here we are going to calculate the feedback output feedback resistor. Okay na? Output resistance we are going to calculate. Connected, this is the feedback network connected across the output. We are going to calculate the feedback output. So here for this feedback I am going to calculate the terms which are related to this network. So here we have an VD, simply we have VD, and the VF feedback connected across the feedback network, the VF, voltage across the feedback is VF, and the IB is the current flowing through the feedback network. R1 is a resistor connected across this output feedback, and the V input is connected across the feedback, and the ROF output feedback here we are going, this is the output feedback net connected, output feedback connected. So IB is the current flowing through this RF, and the V0 is the output voltage, and the I0 is the current across this node, and the IA here, IA is the current across this output resistor R0. So AOL-VD is the voltage gain, and the RI is the input resistor. So I am going to calculate the output resistance by using this circuit. So here we have an X here. So these are having a node X. I am going to apply KCL at this node. Apply. So simply apply KCL. At X. We can get. Apply KCL at X. We can get I0 is equals to I0. This is the I0 now. So I0 is equals to entering current is equals to leaving current. Entering current is the I0, and the leaving current to this X is IA, and the IB. IA is leaving current. This is also leaving current. So I0 is equals to IA plus IB. See here, IB is smaller than IA. Why? Because the input resistance RI is having high input impedance. RI is having high input impedance compared to this R0. Compared to this R0. R0 having a low impedance. Why? So for this purpose, current entering through this having a high priority. That means input resistance having high priority compared to the output current. There is IB is smaller than IA. So here current entering to this input resistance is IA compared to input RI having a high input impedance compared to the R0. Compared to the R0, RI has of an RI is very high compared to the output impedance connected across this terminal is very low. So RI is having high impedance compared to the output resistance or not. So here IA is smaller than IB. So we have write to IA is equals to I0 is equals to IA plus 0 in terms of here the current flowing through this output is very large, very small. Sorry, very small because our output having. We already know on the output side have connected low impedance resistor compared to the input side. So here IA is the input resistance, IB is the output resistance. So IA is small greater than IB. So we neglect the IB here. So I0 is equals to IA. We can get I0 is equals to IA. This is the first equation. So apply here network. Apply KVL law. Apply KVL law at V0. Apply KVL law at V0. So we can get V0 is V0 minus plus to minus means minus I0 or not. Minus I0 or not, and minus AOL-VD minus minus AOLVD. This is AOLVD. So minus AOLVD is equals to 0. Then we can get an V naught term as V naught is equals to, sorry, I have, so I want only R naught term here. So we have an taken out the R naught value to outside. Minus I naught R naught is equals to minus V naught plus AOLVD. So here I want only R naught term here. So here I naught R naught is equals to V naught minus AOL into VD. So I naught R naught is equals to V naught minus AOL VD. So I can have an value I naught R naught is equals to V naught minus AOL VD. V naught minus AOL VD. So I want only I naught value here, V naught minus AOL VD by R naught. Simply you can apply voltage division rule. Apply voltage division rule. Voltage division rule. Voltage division rule at here. Voltage division rule at here. We can get an VF is equals to, this is RF now. VF is equals to V naught into RF. V naught, we simply from the voltage division rule, VF is equals to V naught into RF by V naught into RF by R1 plus RF. V naught into RF by R1. V naught into RF by R1 plus RF from the voltage division rule. So here in the place of an R1 plus RF by RF is equals to beta. So let us assume R1 plus RF by R1 is equals to B. So we can write a BF term as minus B into B naught. Why? Because R1 plus RF by RF means B. So in the place of an RF by R1 plus RF, we can simply write minus B. So here we can have VF is equals to, we can get an VF is equals to VF term as minus V naught. So here V naught and the VF and the VD are the same. That same voltages across. Here also we can consider in the place of an VF, we are going to consider the VD. Why? Because the voltage across is the same. So in the place of an VF, I can write VD. So we can get an VD term as minus beta V naught. So we can have already VD term here, VD here. So in the place of an I naught, we can put I naught is equals to, we have I naught is equal, in the place of an VD we can put an minus B V naught. In the I naught we have an I naught is equals to, V naught minus AOL VD by R naught, V naught minus AOL VD by R naught. So in the place of an VD we can put B V naught. So B V naught plus AOL VD by R naught. So VD means minus V naught becomes plus V naught into B. So taking out common V naught. So taking out common V naught here, 1 plus AOL into B by R naught here, we can get the term I naught is equals to V naught of 1 plus AOL into B by R naught. So here in the place of an we already know V is equals to IR now. So we want our term output resistance R naught. So R is equals to V by I. We can write like this. So R is equals to V by I now. So in the place of an V, we can put simply V naught by V naught is taking common here. V naught, I naught means I naught now. So V naught of 1 plus AOL B by R naught. So V naught gets cancelled. The final equation for this feedback resistance is given as RIF is equals to R naught by 1 plus AOL V. So this is the feedback resistance. So simply we can get an output resistance RIF in terms of an voltage gain. So here simply I can explain once again here. Apply KCL at X. X is the term here, and the I naught is equals to I naught here, and the IA and the IB here. So current flowing through this X is IA and the IB. So I naught is equals to IA plus IB. Here IA is greater than IB, so we neglected the IB. Why? Because the output resistance, output impedance, we already know output impedance connected to this op-amp is very low compared to the input. So for the output feedback, the current flowing through this output feedback is very low. So IB is taken as 0 for the simplification purpose. So IB is taken as 0. So I naught is equals to IA, and KCL, apply KCL at V naught, then we can get an V naught is equals to minus I naught R naught minus AOL VD. So here coming to right side, we can get the equations like this. And equations like this, simply we can apply voltage division rule at VF. VF is equals to V naught RF by R1 plus RF. Simply you can get in the place of an RF by R1 plus RF as V. So in the place of an R1 plus RF by RF is taken as an V. So we have already VD is taken as an VF. For the simplification purpose, the voltage across these input resistance is VF taken as an VF. So in the place of an VD, we can simply put VD. So VD term, we have an VD term is equals to minus V naught. So I naught is equals to V naught minus AOL VD by R naught. So V naught is taken common here. We can get like this, and from this R is equals to V by I. We want output resistance. So R is equals to V by I. We are already V naught. V means V naught. V by, we have an input output current is V naught of 1 plus AOL V by R naught. Simply we can get, and finally feedback resistance is R output by 1 plus AOL V. So tomorrow's class I am going to explain another topic. Thank you.